take some hydrogen gas in a closed container. See, hydrogen gas molecules are present here. When this hydrogen gas sample is irradiated, so here many different hydrogen atoms are present. Every hydrogen atom not necessary to absorb the same type of electromagnetic radiation. They may absorb the different type of electromagnetic radiations. So based on the amount of energy absorbed by every hydrogen atom, the electron goes from the first orbit to the any one of the higher energy orbits. So this is the first orbit of the hydrogen, second orbit, third orbit, fourth, fifth, sixth, seventh, up to so on infinity. So each orbit is known as the energy state. In that, the lowest energy orbit is known as the ground state. And if the electron is always present in the lowest energy state, whenever light strikes the electron takes the amount of energy and it goes to the any one of the higher energy state. So the distance traveled by the electron depends on the quantity of energy it is absorbing. If it absorbs only this much difference of energy, then electron goes from the first orbit to the second orbit. If it absorbs little more amount of energy, goes to the third orbit. Even more, goes to the fourth, fifth and sixth, like that. So the distance of the electron that is traveling depends on the amount of energy it is absorbing. More the energy it absorbs, more the distance it travels, so that go to the even higher energy states. Every time the higher energy states are known as the excited states. When electron absorbs some amount of energy, then we say that electron get excited. Higher energy is always known as the excited form. So then electron goes to the higher energy state. That energy state is now, it is called the excited state, where the electron with higher energy is present. In that, if the electron goes to the second orbit, that means electron first time is going to the out of its orbit and going to the immediately next orbit, next higher energy orbit. That's why here second energy state is also known as the first excited state. If electron straight away goes to the third orbit comes after the second orbit, so it has to cross this excited state. That's why it is known as the second excited state. Then if electron goes to the fourth energy state, then it is known as the third energy state, third excited state, and even after it is called the fourth excited state, and so on. Then when electron goes to the any one of the higher energy state, imagine the electron directly went to the seventh orbit. Imagine electron is here. The maximum time that electron can spend any of these higher energy orbits is 10 power minus 8 seconds. So electron may come back to the any one of the lower energy states. When electron is coming to the lower energy states, that process is known as the de-excitation. So when electron get de-excited, it may come to the any one of the lower energy state. That means electron not necessary directly to come from the seventh energy state to the first energy state. It may initially drop to the sixth energy state, sixth to fifth, fifth to fourth, fourth to third, third to second, second to the one. So that it may travel in the phased manner or it may travel directly. That means, see here, electron is here, it may directly fall down to the first energy state. Or else it may directly fall down up to here, that gives here. See, seventh to the up to here. Then from here again it can directly travel to the first energy state, or to the second energy state, or to the third energy state, or to the fourth energy state. So during de-excitation process, electron not necessarily to come directly to the ground state by releasing all amount of energy, but it releases the amount of energy in the phased manner or completely. So the amount of energy it releases, that decides the de-excitation process of the electron. If it releases only less amount of energy, it goes to the next lower energy state, or else if it releases all the amount of energy, then it falls down directly to the ground state. So electron comes to the lower energy states by releasing the amount of energy. So whenever electron is coming from the any one of the higher energy state to the lower energy states, so when the released energy passes through the prism, then these spectral lines are observed. So Here, as we said that you may ask the question, sir, why these many spectral lines are observed, how many hydrogen atoms are present? See, we are not taking the single hydrogen atom here, we have taken the sample of hydrogen atoms. See, when the sample of hydrogen is irradiated, all the electrons in the different hydrogen atoms goes to the different higher energy levels, and once you remove this one, then higher energy electrons try to come back to the lower energy states. It depends on the different type of the hydrogens. It's not necessary for every hydrogen to release the amount of energy whatever it absorbed earlier. So that whatever the energy is coming, so when this radiation, this is emitted radiation or de-excited radiation, when passed through the nickel prism, so various spectral lines have been observed. Those spectral lines are these. So a series of lines which are observed in the ultraviolet region are named as the Lyman series. So Lyman series of lines obtained when electron from any one of the higher energy state when fall down directly to the ground state. So lot of amount of energy it is going to release. So that series is known as the Lyman series, and the region, these series of lines are observed in the ultraviolet region, that means higher frequency region. That's why this Lyman series is always having the higher energy. And next one, if electron do not fall to the ground state but fall up to the second energy state. So when electron is de-excited from any one of the higher energy state to the up to second energy state, a series of lines observed in the visible region, these are known as the Balmer series of lines. Initially, among all these series of lines, only these Balmer series of lines were observed by the Balmer. Reason is these are visible to the naked eye. Remaining radiations, remaining lines are not visible to the naked eye. They were observed later. Next, when electron is coming back to any one of the higher energy level to the up to third energy level, the series of lines observed in the near IR region known as the Paschen series, and up to the fourth energy level they are known as the bracket series. These are visible in the middle IR region, and up to the fifth energy state the series of lines are separately named as the Fund series. They are observed in the far IR region. Even Humphrey series also there, but that is not necessary for us to discuss over here. Now, in any series, whatever the series it may be, the first line of this series is always known as the alpha line, second line is known as the beta line, third line is known as the gamma line, delta, epsilon, and so on. So, for Lyman series, H alpha line means N1 is always 1, means lower energy state in the case of the Lyman series is always is equals to, N1 value is always equals to 1, but N2 value for the Lyman series changes. N2 may be 2, 3, N2 stands for the higher energy state. So higher energy state may be 2, 3, 4, 5, 6 up to so on, up to infinity. So if N2 equals to 2, that is called as the first line. See, for first line, N1 equals to 1, N2 equals to 2. For second line, N1 is always equals to 1, but N2 is equals to 3 like this. And in the case of the Balmer series, the N1 value means Balmer series of lines are observed in the up to N equals to 2. So N1 value, that means lower energy state for the Balmer series is equals to 2 only. Then N2 means higher energy states. It may be 3, 4, 5, 6, 7 up to so on. And in the case of the Paschen series, N1 is equals to 3, N2 equals to 4, 5, 6 up to so on. And in the case of the bracket series, N1 is equals to 4, N2 is equals to 5, 6, 7 up to so on. And in the case of the Fund series, N1 is equals to 5, whereas N2 equals to 6, 7, 8, 9 up to so on, infinity. So this is the hydrogen spectrum. Now let us discuss how many number of spectral lines observed in the hydrogen spectrum and how to calculate this number of spectral lines in the hydrogen spectrum. Number of spectral lines. So here calculations depends where the electron is de-excited. If electron is coming back from any one of the higher energy state to the directly to the ground state. So here when electron is de-excited to the ground state, then number of spectral lines number of spectral lines is equals to, we can write down that sigma delta n, or else sigma n2 minus n1, or else the same formula we can write down as n into n1 n into n minus 1 by 2. Here n stands for the higher energy states, where n equals to higher energy state, number of the higher energy state. That means imagine when electron is de-excited from the fifth energy level to the ground energy level, then how to calculate the number of spectral lines? So let us use this formula. Later we shall come back to that formula. n2 minus n1, that means 5 minus 1. So 5 minus sigma value, if you use it, sigma means all the differences we have to calculate. So 5 minus 1 plus 4 minus 1 plus 3 minus 1 plus 2 minus 1 plus 1 minus 1. So 5 minus 1 is equals to 4. 4 minus 1 is equals to 3. 3 minus 1 is equals to 2. 2 minus 1 is equals to 1. 1 minus 1 is equals to 0. Total value 4 plus 3 7. 7 plus 3 equals to 10. So that we can see 10 spectral lines. So this is the calculation where we have to add all the difference values if you use this formula. What if you use this formula, how you can get directly the answer? From where the electron is coming, what we have said, fifth energy level. So use the n value equals to higher value. So 5. 5 of 5 minus 1. 5 minus 1 means it is equals to 4. So that 5 of 5 minus 1 divided by 2. 5 minus 1 4. 5 into 4 by 2 equals to 20 by 2 equals to 10 spectral lines directly. So the question is how 10 spectral lines are observed. See here, 5 to directly first energy level 1 spectral line, and 5 to the 3 1 spectral line, 4 to the 3 1 spectral line, 3 to the 2 1 spectral line, and 3 to 2 also there. Means all the lines together we have to calculate. Means Lyman series lines, Balmer series line, Paschen series, bracket series, all the lines we have to see that. See here only series we don't see is fund series of lines we don't observe. So 5 to 1 here is there, 5 to 3 is possible, 5 to 2 is possible, 5 to 1 is possible. Afterwards, see 4 to 3 is possible, 4 to 2 is possible, 4 to 1 is possible. Next, see 3 to 2 is possible, 3 to 1 is possible. Next, 2 to 1 is possible. So by adding all these values, we can get the 10 spectral lines. Means combining all these spectral lines, we can calculate like this. If you use the formula for this, this is applicable when the electron is directly excited to the ground state. It is coming to the Lyman series. Then second one is when electron is de-excited to any one of the energy levels, then number of spectral lines equals to n2 minus n1 into n2 minus n1 plus 1 divided by 2. So n2 is equals to higher energy state, n1 is equals to lower energy state. That means, see, now I am not talking about that electron is from the fifth energy level coming directly to the first energy level. So what I am saying is now electron is coming from the fifth energy level to the second energy level. So how many spectral lines are observed? Then n2 is equals to 5 coming up to the 2. So 5 minus 2. This is 5 minus 2 plus 1 divided by 2. So this is equals to 3 of, so 3 plus 1 4 divided by 2. So this is equals to 12 by 2 equals to totally 6 spectral lines are obtained. So when electron is de-excited to the any one of the energy levels, apart from the ground state, you can use this formula directly to calculate the number of spectral lines. Then, number of spectral lines. In a series, you take any series, number of spectral lines is equals to n2 minus n1. So what is the difference among all this? This is for when directly fall down to the ground state, which includes all these spectral lines. This is to the any one of the energy levels, again including all these spectral lines. This means spectral lines of the all these series. This is only for a particular series. Imagine when electron is de-excited from third energy level to the ground energy level, the number of spectral lines obtained in the Lyman series only I am discussing, 3 to 1. So when electron is de-excited from the third energy level to the ground energy level, find the number of spectral lines obtained in the only in the Lyman series. So 3 minus 1 is equals to 2. Apart from this, if you use any of this formula, you will get the another answer. How means? See, 3 to 1 spectral line, again 2 to 1 spectral line, totally 2 spectral lines we are getting only in the Lyman series, that is 3 minus 1 equals to 2. If Lyman series is not mentioned, we have to include this value also. Balmer series of line also to be calculated. So like this, a number of spectral lines can be calculated. Now let us see how to calculate the wave number, energy. So calculation of wave number and wavelength. So Balmer has given a formula to calculate the wave number and wavelength, because Balmer knows only this series of lines. So based on this, he has given one formula, that is nu bar equals to 1 upon lambda equals to 109,677 into 1 upon 2 square minus 1 upon n square per centimeters. This is applicable only to the Balmer series of lines, because Balmer was not knowing about the other series do exist. That's why he has directly taken the 2 value here. This is lower energy state. N means any one of the higher energy state. By substituting these values, we can get the wave number or wavelength. Then later Rydberg modified this equation and tried to apply to the other series of lines using the formula nu bar equals to 1 by lambda into equals to 109,677 into 1 upon n1 square minus 1 upon n2 square per centimeters. So this value later replaced using the directly the constant, that is what called the Rydberg constant for the hydrogen atom, into 1 upon n1 square minus 1 upon n2 square per centimeters. This is only for the hydrogen, where n1 is equals to lower energy state, n2 equals to higher energy state. Now, what if hydrogen-like species, if you would like to apply this? Hydrogen-like species means He plus, Li2 plus, Be3 plus, etc., which are single electronic systems. So for this means, then it is not same as in the case of this hydrogen spectrum. That means this formula, so that it has to be modified because atomic number is included. So that we can write down this formula as nu bar equals to 1 upon lambda equals to RH, which is called as the Rydberg constant, into 1 upon n1 square minus 1 upon n2 square into z square per centimeters. This can be this formula can be used for all single electronic systems, including hydrogen atom. Now, If you want to calculate the wavelength, just inverse this, because nu bar equals to 1 upon lambda, the entire value has to be reversed, so that we will get the lambda value. Then how to include energy format in this particular equation? We know that delta E equals to Hc nu bar. So nu bar place, nu bar is equals to delta E by Hc. So this value if we substitute here, then we'll get the formula delta E by Hc is equals to RH into 1 upon N1 square minus 1 upon N2 square into Z square. Here units we cannot write down because energy value, whatever the energy value here you are taking, if you take the joules, it will be joules. If you take the electron volt per atom, it will be electron volt per atom. So that delta E is equals to RH Hc into 1 upon N1 square minus 1 upon N2 square into Z square. So H value, C value, R value constant. By taking all these constants, we can get the delta E value as 13.6 into 1 upon N1 square minus 1 upon N2 square into Z square electron volt per atom. By multiplying all these values, we can get the electron volt per atom. So here one important thing is, see, N2 is equals to infinity. That means the electron is in the first orbit and I am taking the electron to the infinite orbit. Infinite orbit means I am going to remove the electron from the hydrogen atom. So if N2 equals to infinity and N1 equals to 1, then delta E equals to 13.6 electron volt per atom. That means that is what called the ionization energy. The energy required to remove the electron from the hydrogen atom is called as the ionization energy, that is 13.6 electron volt per atom. Now let us compare the both the wavelengths as well as the energies of one spectral lines with the another spectral means one series of spectral lines with the another series of the spectral lines. So let us see the comparison of energy. Energy or wavelength, both we can take here, of various series lines. If you observe one important thing in the hydrogen spectrum, one basic thing we should not forget. See here, the difference in energy between the first energy state and second energy state is too large. And going to the second and third is the value decreased. 3 to 4 still decreased. 4 to 5 still decreased. Here still decreased. Here still decreased. And afterwards the orbits almost becomes continuous. That means they merge with each other. So the energy gap becomes almost negligible. So energy transition is very high. Energy gap. Next here, next here, next there. So that if you see that energy gap between any spectral lines, so which is carrying the more energy gap? Lyman series, next Balmer series, Paschen series, and bracket series, Fund series of lines. That is the reason why you can see that Lyman series of lines are visible in the ultraviolet region, visible infrared, near infrared, middle infrared and far infrared, so that almost wavelength increases and frequency decreases. Now if you compare the within the series, the lines, within any series, the last line, here it is the last line, and in this case let us imagine this is the last line, here this is the last line, here this is the last line. So within any series, the last line, that is what called as the limiting line. The last line has highest energy or frequency or lowest wavelength among all other lines. So that means this line carries more energy because the energy gap is more. So obviously when electron is coming from the any one of the infinite energy level to the ground energy level, since it went to the higher energy state, while coming back also it will release more amount of energy. That's why the last line will have the highest energy in this Lyman series. And when it comes to the Balmer series of lines, when you compare only Balmer series, again here also last line carries more energy. Paschen series also last line carries the higher energy. So for last line, the N2 value is always equals to infinity. So this is infinity to the ground energy level or second energy level or third energy level. The last line of any series carries the higher energy. Higher energy means higher frequency. When frequency increases, automatically wavelength gradually decreases. So lowest wavelength, or you can write down this one as a shortest wavelength. Then how to compare this one when it is there? Let us take only, I am taking the Lyman series. E infinity to E1 is greater than any other lines in the case of Lyman series. In the case of Balmer series, E infinity to E2 is greater than any of other lines of the Balmer series. Paschen series, E infinity E3 is having the higher energy than the any of the other lines of the Paschen series, and so on. Now let us compare one series of lines with the another series of lines. See that this energy gap is always higher. Actually, I have written these values a little bit larger to make sure the diagram is visible to write down all this. But actually, this entire ends within this area only. That means this gap is even more than this entire region. So that's why the first line of the Lyman series always having the highest energy than any energy of the any line energy of the any series. So here the first line of Lyman series has highest energy than any line of other series. See that this first line we are comparing with other lines, not within the Lyman series. Within the Lyman series, last line carries highest energy. But when with this first line is compared, then this first line itself is carrying the more energy than the any other lines of the other series. That means automatically second energy is more than this one. Third energy is more than any other. That means here you can say that E1, E2 is greater than E2, E3 greater than E3, E4 greater than E4, E5. See, this is the first line is there. 1 to 2 gap is there. This is the highest energy compared with any other transitions. Or else you can write down E2, E1 energy is more than, for example, E infinity to E2. Even this is having less energy than this one. Next one, E infinity to E3. E infinity to E4, E infinity to E5. That is what I am going to tell. Any line of the other series shall have the less energy compared to the first line of the Lyman series. That's why in this Lyman series, this last line is called the line with highest frequency and lowest wavelength. And first line is called the lowest frequency and highest wavelength within the Lyman series. But when compared to the other series, the first line is carrying the more energy than the other series of the lines. And in these calculations, we need to use 1 by lambda is equals to 1 by Usually we need one particular term while solving the questions, that is 1 by RH, Rydberg constant value they used to ask. So 9 12 angstroms, this may be helpful in solving the questions. This is what we discussed as emission spectrum of the hydrogen. Starting we said that when hydrogen sample get irradiated, so that electrons goes to the higher energy level. So that time if you get the absorption spectrum, that absorption spectrum is giving the single line in Lyman series. Single dark line in the Lyman series. That means whenever initially you have taken the hydrogen sample, the electron is present in the first energy state, that is ground energy state. When suddenly energy is given, it has to move from the first energy state to any one of the higher energy state directly. That means the first energy state to any one of the higher energy state means all the series of lines must observe only in the Lyman series, so that it also clearly says that the electronic excitation takes place directly in a single phase, not in the stepwise manner. That means electron either directly go to the second energy level or to the third or to the fourth. Not like that going from the 1 to the 2, 2 to the 3, 3 to 4, 4 to 5 is not possible. So stepwise excitation is not possible. Directly it goes to any one of the higher energy state. Why? Because it is taking the energy at a time. But while coming back, source is not there, so that while de-excitation, electron may come to the any one of the lower energy levels by releasing the amount of energy. So dear students, I hope you understand this class. We shall meet in the next class. Thank you.